the reaction that refused to stay contained. At first, it was believed to be perfectly controlled, safely isolated within boundaries carefully calculated by experts who trusted equations, protocols, and past experience without hesitation. The reaction behaved exactly as expected in tests, responding only where it was allowed, only when triggered, and only under conditions that had been reviewed, approved, and repeated countless times. That confidence is what made its eventual spread so shocking, because nothing in the data suggested it would ever escape. To understand why this reaction matters today, we need to understand how containment is defined in chemistry. Containment is not about stopping reactions. It is about limiting where they occur. Barriers, vessels, membranes, and environments are designed to guide chemistry, not eliminate it. As long as reactions remain inside their assigned space, they are considered controlled. That assumption underpins laboratories, factories, and entire industries. Modern systems depend on this logic. Energy is stored inside batteries. Reactivity is confined inside reactors. Hazardous compounds are sealed behind layers of material and regulation. Containment creates the illusion that chemistry can be told where to exist. As long as the reaction stays put, the system feels safe. In early experiments, this reaction complied perfectly. It activated on command. It shut down when input stopped. Sensors confirmed boundaries held. No leaks, no drift, no unexpected byproducts. The reaction earned trust by behaving politely, and polite chemistry is rarely questioned. This is the first narrative beat, a reaction that followed every rule it was given. It did not spike. It did not spread. It did not resist control. Each successful run reinforced belief that containment was absolute. Engineers relaxed. Design scaled. Margins narrowed. Confidence replaced caution. The second beat followed with expansion. The reaction was pushed into larger systems, longer run times, higher densities, more complex environments. Still, containment held, at least visibly. What went unnoticed was how conditions inside the boundary were changing. Gradients formed, stresses accumulated, interfaces aged. Chemistry adapted quietly. The third beat began invisibly. Molecules at the edge of containment behaved differently. Energy leaked not as heat or pressure, but as opportunity. Microenvironments formed where the reaction could persist briefly outside its intended zone. Not enough to trigger alarms, enough to learn. This is where the story begins to tighten. Because chemistry does not need permission to move. It only needs a pathway. And once a reaction discovers that a boundary is conditional rather than absolute, it does not stop at the line humans drew. It tests it, again and again, until containment becomes suggestion instead of rule. Once the reaction discovered that containment was conditional, chemistry began doing what it always does when boundaries weaken. It explored every available route with patience, repetition, and absolute indifference to human intention. It did not escape all at once. It leaked in moments, in fragments, in configurations too small, too brief, and too subtle for instruments designed to detect failure rather than adaptation. At first, these excursions seemed insignificant. A transient molecule here, a fleeting byproduct there. Nothing sustained, nothing measurable at scale. The reaction still behaved inside its container, and so the system was judged safe. But chemistry does not require permanence to learn. It only requires exposure. This is where the reveal deepens. Containment relies on materials remaining unchanged. Seals must stay tight. Membranes must stay selective. Surfaces must stay inert. But no material is static. Under heat, pressure, radiation, and time, barriers age. They develop microfractures. They adsorb molecules. They change polarity. And each change rewrites what containment means at the molecular level. Inside these altered boundaries, the reaction began to exploit gradients, concentration differences, temperature variations, electrical potentials. Energy always moves downhill, and chemistry followed that slope precisely. What engineers saw as negligible variation, the reaction treated as invitation. The early conflict forms here, because containment was never designed for learning systems. It assumed reactions were passive, predictable, content to remain where placed. But this reaction was dynamic. It responded to environment. It adapted to constraints. Each small escape made the next one easier. As scale increased, the problem intensified. Larger systems created longer boundaries. Longer boundaries created more weak points, more interfaces, more chances for chemistry to test conditions. The reaction did not need to break the container. It only needed to blur the definition of inside and outside. Human response followed familiar patterns. Additional layers were added, barriers thickened, controls tightened. Each fix treated containment as a structural problem. But chemistry was solving a different equation. Not how to break walls, but how to use them. What nobody expected was persistence. Once the reaction established activity beyond its intended zone, it did not retreat. It stabilized. It found niches. It integrated with surrounding chemistry. Containment had failed not catastrophically, but philosophically. The reaction was no longer something that happened in a place. It had become something that happened across boundaries. And that shift made traditional control meaningless. This is a moment where tension truly builds. Because a containment is no longer absolute, then safety becomes probabilistic. And probabilistic safety always trends toward exposure. When chemistry is given enough time, this is where the conflict fully ignites. Because once a reaction begins operating across boundaries instead of within them, the very concept of containment collapses into a fragile approximation rather than a rule. What engineers once treated as a closed system slowly reveals itself as porous, dynamic, and deeply entangled with its surroundings, and chemistry takes full advantage of that entanglement. As a reaction stabilizes beyond its original limits, it begins influencing neighboring systems. Not violently, not dramatically, but persistently. It alters local chemistry, just enough to make those environments more favorable for its own continuation. Interfaces change behavior. Materials age differently. Adjacent reactions shift balance. Containment no longer separates systems. It connects them. The buildup intensifies here. Because a reaction is no longer isolated, it starts forming feedback loops. Escaped molecules modify surfaces. Modified surfaces ease further escape. Each cycle reinforces the next. What began as leakage becomes self-supporting activity. Chemistry builds momentum without ever crossing a single dramatic threshold. Human systems struggle to respond. Controls are calibrated for breaches, not diffusion. Sensors look for spikes, not gradients. Alarms expect sudden failure, not gradual integration. By the time data confirms spread, the reaction has already woven itself into the surrounding chemical landscape. Reversing it would require reversing the environment itself. This is an emotional peak. Because containment did not fail due to negligence. It failed because it was built on a flawed assumption. That chemistry respects borders. That reactions are content to remain where placed. That walls are more than temporary agreements. Chemistry never accepted those terms. As intervention escalates, unintended consequences multiply. Barriers added to stop the reaction disrupt other processes. Suppressing one pathway activates another. Energy redirected here appears there. Each attempt to force confinement increases system-wide stress. Complexity rises. Predictability falls. Control dissolves. At this stage, the reaction is no longer a problem. It is the messenger. It reveals that the system was never truly closed. That containment was always conditional. That chemistry has been interacting across boundaries the entire time, waiting only for conditions to favor persistence. The realization is unavoidable now. If a reaction can learn to exist beyond its container, then safety is not a property of walls. It is a property of design humility. And without that humility, every boundary eventually becomes negotiable. This prepares the ground for the final reckoning. Because once chemistry escapes containment conceptually, no amount of physical reinforcement can restore the illusion that it was ever truly confined. The climax is not the escape. It is the realization that containment was never absolute. The reaction did not break free. It was never fully trapped to begin with. Boundaries only delayed interaction. They never eliminated it. Chemistry obeys gradients, opportunities, and time, not intentions or diagrams. This is the central truth. Containment works only when systems remain simple. Once complexity increases, boundaries become negotiable. Materials age, interfaces evolve, microenvironments emerge, and chemistry moves wherever conditions allow it to persist. While slow reactions, they do not stop them. The resolution is not stronger containment. It is different thinking. Systems must assume interaction, not isolation. Design must anticipate leakage, diffusion, and adaptation. Safety must be layered with acceptance that chemistry will explore every available pathway eventually. Modern relevance makes this unavoidable. Energy storage, chemical manufacturing, biotechnology, environmental systems, all rely on containment assumptions, and all operate at scales where chemistry has time to test limits patiently. What stays contained today may integrate tomorrow. Once this is understood, control is redefined, not as preventing movement, but as managing interaction, allowing chemistry to dissipate safely instead of forcing it to remain confined, designing for escape routes instead of denying escape exists. The reaction that refused to stay contained did not defy science. It exposed an outdated expectation that chemistry can be boxed permanently. It cannot. It can only be guided, slowed, and respected, because chemistry does not ask where it is allowed to exist. It asks where it can, and given enough time, it will always find the answer. Sometimes the smallest shift in perspective becomes the beginning of a new future. The